1. Revolutionizing soft robotics. Control with just one image. MIT AI breakthrough. 2. MIT's AI breakthrough. Robots that learn through vision. 3. Revolutionizing soft robotics. Precision control with neural Jacobian fields, NJF. 1. Revolutionizing soft robotics. Control with just one image. MIT AI breakthrough. Imagine a future where robots can navigate through tight spaces and adapt to rough terrains with ease, all by simply looking at a picture. That's exactly what researchers at MIT have achieved with their groundbreaking development of a low-resource AI system capable of controlling soft robots using just one image. Traditional robots used in industries and hazardous environments are relatively straightforward to control and model due to their rigid structures. However, these limitations prevent them from operating efficiently in confined areas and uneven surfaces. In contrast, soft robots, inspired by biological organisms, offer superior adaptability to various environments and can maneuver in hard-to-reach spots. Achieving such flexibility typically requires a sophisticated array of onboard sensors and intricate models tailored specifically for each robot design. To address this challenge, MIT's researchers have introduced a novel, resource-efficient approach. They've developed a simplified deep learning control system that enables soft, bio-inspired robots to interpret commands from a single image alone. This innovative method significantly reduces the complexity of the control system, making it more accessible and practical. According to phys.org, https://physics.org, and TechExplore, https://techexplore.com/news/2025-07-deep-soft-bio-robots-camera.html. The study was published in the prestigious journal Nature. By training a deep neural network on a mere 2 to 3 hours of multi-angle images of various robots executing random commands, the scientists managed to teach the network to deduce the full range and shape of the robot's mobility from a single snapshot. Traditional machine learning control systems, on the other hand, necessitate customized and expensive motion systems, thereby limiting their applications and making prototyping impractical. This new approach liberates robotics hardware design from the constraints of manual modeling. It eliminates the need for precision manufacturing, extensive sensor capabilities, costly materials, and reliance on conventional, rigid components. Instead, the system relies solely on vision, enabling high-precision control across a diverse array of robotic systems, including a 3D, printed pneumatic hand, a 16-degree of freedom Allegro hand, a soft auxetic wrist, and a budget-friendly Poppy robot arm. However, there are some limitations to consider. Since the system operates based on visual input alone, it may not be ideal for tasks requiring fine motor skills and tactile feedback. Performance could diminish in scenarios where visual cues are insufficient. To overcome these challenges, researchers recommend incorporating additional sensors and tactile materials that would allow the robots to execute a broader range of complex tasks. Furthermore, there's potential to automate the control of various robots with minimal or no embedded sensors. But here's where it gets controversial. Could this technology eventually replace traditional sensors entirely? What ethical considerations arise when we rely so heavily on visual data for robotic control? We look forward to seeing how this innovative approach evolves and what new possibilities it opens up in the field of robotics. 2. MIT's AI breakthrough, robots that learn through vision. MIT researchers have shattered conventional robotics paradigms with a vision-based AI that learns to control any robot through observation alone, no sensors or pre-training required. Imagine machines gaining human-like self-awareness by simply watching themselves move. Unlike traditional systems demanding precision-engineered robots and exhaustive sensor arrays, this breakthrough leverages ordinary cameras to map a robot's movement in 3D space. The AI constructs a visual-motor Jacobian field, a dynamic model linking visual data to motor controls, enabling it to autonomously master dexterous tasks like grasping objects within hours. Lead researcher Cija Lesterly compares it to human learning, like wiggling your fingers to understand movement. Our system experiments randomly to self-discover control. But here's the controversial part: this eliminates the need for costly engineering or massive training datasets, potentially democratizing robotics. Critics argue this approach risks oversimplifying complex environments, Could occlusion or chaotic settings cause catastrophic failures? The team validated their framework using consumer-grade cameras filming robots for 2 to 3 hours, then applied it across diverse architectures including flexible soft robots. Results in Nature show superior accuracy over existing methods, even with visual obstructions. While proponents hail this as the dawn of adaptable, low-cost automation, skeptics question scalability. Can this truly replace domain-specific sensor fusion in critical applications like surgery? What's your take? Revolutionary leap or overhyped experiment? Share your perspective below. 3. Revolutionizing soft robotics. Precision control with neural Jacobian fields, NJF. Imagine a world where robots are as gentle as a surgeon's touch, as adaptable as a contortionist, and as precise as a master craftsman. This is the promise of soft robots, and it's a future that's closer than you might think. But here's where it gets controversial. While soft robots hold immense potential, they've been held back by one major challenge: controlling their movements with the precision needed for real-world applications. But what if we could change that? Soft robots, unlike their rigid counterparts, are designed to be flexible and adaptable. For instance, a soft robot assisting in surgery would be less likely to cause harm due to its gentle nature. Similarly, a soft robot navigating tight spaces would be far less likely to get stuck, thanks to its ability to bend and squish around obstacles. However, despite these advantages, soft robots have remained largely confined to research labs. Why? Because controlling their movements has been a nightmare. Traditional robots, with their rigid components, are easier to predict and control. But soft robots? They tend to flop around unpredictably, making it incredibly difficult to adjust their actuators for precise actions. And this is the part most people miss. If you can't guarantee precision, you wouldn't want these robots performing delicate tasks like surgery. But hold on to your hats, because a group of brilliant minds at MIT might just have the solution. They've developed a deep learning-based approach that can predict how soft robots will respond to control inputs with astonishing accuracy. And the best part? Their system doesn't require a massive, expensive hardware setup. A single camera is all it takes. This groundbreaking approach is called neural Jacobian fields, NJF. Instead of relying on traditional modeling techniques, physical sensors, or motion capture systems, NJF uses a vision-driven, self-learning control system. Here's how it works. During training, a robot is recorded performing random movements using a multi-camera setup. From these visual inputs alone, NJF learns both the robot's shape and how different control signals affect its movement. Once trained, the robot can operate autonomously and accurately in the real world, even with just a single, monocular camera. In tests, the system achieved less than 3 degrees of error in joint motion and sub-centimeter accuracy in fingertip placement, all without embedded sensors. The implications of this work are enormous. Soft robots equipped with NJF can adapt to messy, unstructured environments like farms, warehouses, or disaster zones, using only visual feedback. This opens the door to more creative and experimental hardware designs, as engineers are no longer bound by the limitations of traditional modeling techniques. It's a shift away from hard-coded control logic and toward learning-based systems that can adapt and improve over time. By giving robots an internal sense of how their bodies work, the system allows for more fluid and natural movements. And that could bring us closer to a world where robots are flexible, adaptive, and accessible to all. But here's a thought-provoking question. As we move towards a future dominated by soft robots, how will we ensure their safety and reliability? Will we need new regulations and standards, or can we trust in the adaptability of these learning-based systems? What do you think? Share your thoughts in the comments below, and let's spark a lively discussion on the future of soft robotics.